Audio Jungle. Audio Jungle.
So here we have a types of strain, right? Types of strain. So here basically we'll have three types of strain. Three types of strain. It's called linear strain first. Linear strain. Second one is called lateral strain. And one is called volumetric strain, right? Linear strain, lateral strain, and volumetric strain. Now one by one we'll see what is the linear strain. So linear strain. So for the linear strain, easily we can understand. Suppose we are taking here one straight bar, okay, and in this linear strain, that also I have to mention. Suppose this linear strain. So here two types of strain we have to talk. One is called tensile strain. Another is called compressive strain. Okay. Compressive strain. All right. Now in this linear strain, we'll talk first tensile strain. All right. Now what is the tensile strain? By the word only you can understand the basically because of the tensile load. Suppose this is the bar, this is the bar, this bar length is nothing but actual length is nothing but L. Now for this particular bar, suppose this bar we have already having length L here, but also it is applied with load. And what is that load? It's a tensile load. I can say this bar is what, this side it is fixed, this side it is fixed, and we are having tensile load P. This is the tensile load P. Once tensile load P is what applied, so earlier the length was L, but because of the load P, delta L length is what increased. Obviously it's a tensile load, so elongation will be there. So for the tensile strain, we'll have a tensile load here, and because of the tensile load we have a elongation. Okay, elongation means increment in length. Okay, increment, see the length is what increased here. Now if you see the complete bar, so this complete bar is nothing but something like this. See, this is the complete bar. Okay, and obviously up to here this is nothing but L, and this is nothing but delta L. So I can say what is the initial length here? Initial length it was L. What is the final length? It becomes L plus delta L. What is change in length? It's nothing but final minus initial, that is L plus delta L minus L. Final minus initial. What is the change in length? It's nothing but delta L now. Okay, What is the now we are talking about the tensile strain. So what is the tensile strain? Tensile strain is nothing but initial length or actual length, or initial length meaning is same, actual length or initial length, okay, that meaning is same. What is the actual length? uh, Change in length, sorry, this is the change in length. This is nothing but change in length divided by actual length, means delta L by L. This is called tensile load, tensile strain. Okay, so tensile strain, obviously this strain is what denoted by epsilon. So tensile strain also called delta L by L. This will be positive with sign. Why? Because length is what increasing here, no? If you talk about the compressive length, compressive strain, this is the tensile strain. I have shown you two types of linear strain we have. This linear strain also called as longitudinal strain. Okay, there should not be any doubt. This linear strain also called longitudinal strain. Okay, always remember. And longitudinal strain will have a two types, tensile strain and compressive strain. Because in tensile strain, tensile load will be there, and always remember, tensile load will always elongate the length. So there will be elongation in length here. Okay, there will be elongation, which means increment in length. You have seen in the diagram. Now if you see, the initial length was L, final length becomes L plus delta L. What is the change in length? It becomes L plus delta L minus L. If you see the change in length, it becomes delta L now. What is the tensile strain then? Change in length divided by actual length or original length, which is nothing but delta L by L. That is completely tensile strain. Always remember, this will be positive because change in length delta L is what positive. But at the same time, if we are talking about the compressive strain, okay, at the same time, if we are talking about compressive strain, what is the mean of compressive strain? Okay, so in case of the compressive strain, obviously, suppose this is the bar now. Okay, this bar is nothing but length is what? L. Okay, now for the same bar we have here, see, something like this. But now once you apply load, and that load is nothing but compressive load, the actual length was something like this. This was the actual length, but because of the compressive load here, compressive load P, this length becomes only uh, L, and this length is what reduced by delta L because of the compressive load. So this length becomes only L minus delta L. Yes or no? Because total length was L. So from
हेलो सर, आवाज नहीं आ रहा है सर। हेलो।
so compressive load, and obviously because of the compression, there is the shorten of length, means length will be decreased. If it is shortened of length, then obviously negative sign will come. Okay, now coming to this, what is the initial length?
हेलो।
It is L. What is the final length? It becomes L minus delta L. What is change in length, it becomes final minus initial. You will get minus of delta L. What is compressive strain? It's a sigma C. Change in length divided by original length, delta L by L. So sorry, this is not sigma C, this is epsilon C. By mistake I have written. So epsilon is the symbol for the longitudinal strain. Okay, epsilon is the symbol for longitudinal strain. If it is tensile, so sigma T you can write, and if it is compressive, you can write sigma C. It's your choice what symbol you want to give. Here sigma T you can write, epsilon T you can write epsilon T and epsilon C. So compressive strain is always negative sign you have to take. Why? Because that length is what decreasing now. All right, now in both cases you can check here. I'll take one more example. Like suppose this is the bar, now. Just say this length is L and this width is nothing but B now. Okay, but suppose in this bar, now this bar is what connected with the tensile load, so obviously length will be increased, and once length is what increased, so what will happen, let me show you. Once length will increase, then what will happen? See, length is what increase
Weight
for
will
but
reduce.
width will be reduced, right? Very good. So length, it is L, but this becomes delta L. What is the overall length now? It becomes L plus delta L. But what about width? It was capital B, now it becomes small b, I can say. It becomes small b. That simply you can understand in this way. So the overall idea is, now if length is what increasing, the width will be decreasing at the same, and when it is happening, when there is the tensile load, because of the tensile load only it is happening. But the same bar also you can say, this bar width also can increase now, but at the same time length will be decreased. See, if it is compressive, so both side compressive force will be there, then this width will be increasing, so that time width will be what, you just say B dash. That means B dash is always greater than B, and this B is greater than small b. Okay, so the point is, if there is compressive load, so more width will be there, and this length will be L minus delta L. Means length is what decreased. But so what is the point? What points you got? Length increases, width decreases, or length decreases, width increases. This point you understood, right? Based on this analysis only, we have a lateral strain. Okay, based on this analysis only, we have a lateral strain. What is the lateral strain now? So you can say lateral strain. So lateral strain is nothing but, it's also called, okay, lateral strain, it's also called transverse strain. It also called transverse strain. Okay, and what is the a mean of the lateral strain always it's perpendicular to the direction of applied load. Okay, it's perpendicular it's perpendicular to applied load. Okay, perpendicular to applied load meaning is very simple. See, as I told you, if this is the bar, okay, this bar length is what? L. This bar length is nothing but L, right? Now if this bar is what subjected with the load, and here suppose you just fix this end and this side it is subjected with the load, so length will be increased. Actual length is what? L. Okay, and this is delta L. Length will be increased, but what happens to the width of this bar? It will be decreasing. How much and how it looks like, we can show by this way. See, you can show by this way. Wait, you can show this bar by this way. The bar size width will be decreasing like this. Okay, and if you show this exactly, so this bar will be like, if circular bar is there, then this will be like this. So if you, again wait, if you concentrate here, so what you will get? Because load is what acting axially, okay, and it's a tensile load, so obviously length will be increasing. So length will be increasing something like this. But if you check perpendicular to the load, where is the perpendicular to load? This is the tensile load here. So where is the perpendicular? Perpendicular means along the load. This is longitudinal. Perpendicular means in this way. So in this way, if you check, the width is what? Decreasing. Okay, the width is what? Decreasing. So lateral strain, also known as transverse strain, and this transverse strain always takes place at right angle to the direction of applied load, is known as lateral strain. Okay, is known as lateral strain. Now in terms of diameter, if you say, because this is, I told you, this is the circular rod, if this is the circular rod, so what is the actual, diameter? Actual diameter of this rod, is nothing but capital D. Okay, actual diameter of this rod is nothing but capital D. That means this is the circular rod here, so this is the constant diameter here. See, something like this, but length is what? Increased, then diameter will be decreased. Okay, suppose the now becomes something like this. Length is what? Increased, but diameter is what? Decreased, because of this tensile load P. So now what is this diameter? I can say capital D minus delta capital D, means this delta D is the decrement in diameter, right? So what is the lateral strain? Lateral strain is nothing but, in this case, change in diameter divided by actual diameter. Actual diameter, right? So lateral strain, if you see the initial diameter, D, final diameter, it becomes capital D minus delta D, change in diameter, it's nothing but d minus delta d minus d. dd cancel out, what you will get? Minus of delta d, right? Minus of delta d, that is change in diameter. So what is the lateral strain? It's nothing but change in diameter, which is nothing but magnitude only, delta d by d, actual diameter. So this is nothing but lateral strain. Diameter, if you check, because load you are applying longitudinally, this is the longitudinal axis, this is the longitudinal axis. Load you are applying longitude along the longitudinal axis, but this one perpendicular to longitudinal axis, we have a lateral axis, this one. Okay, this is the lateral, or sometimes called transverse. So in transverse direction or in lateral direction, whatever the change in diameter divided by original diameter will be called as a lateral strain. I think, hope you understood this. At the same time, we'll talk
Yes.
about the Poisson ratio also. Now the same point I can discuss is the Poisson ratio. What is the Poisson ratio? It's a Poisson ratio. Okay, it's a Poisson. It's a Poisson's.
Lateral upon longitudinal, no, sir?
Yes. It's a Poisson ratio. So Poisson ratio, just now you have seen lateral strain and longitudinal strain. Longitudinal means linear strain basically. So you can write Poisson ratio, it is denoted by, okay, it is denoted by mu. So mu is nothing but, that formula I will give. So it's nothing but lateral strain by longitudinal strain. As you know, lateral strain by longitudinal also called linear. So in few books, mu also given as lateral strain divided by linear strain also. Okay, always remember longitudinal by linear strain. Now in diagram, how you will see it for the Poisson ratio, it's very simple. You can take this bar. This bar is simple prismatic bar, just like this. Now this bar is what? Subjected with the load, tensile load. So obviously this bar length will be increased something like this. So in this direction where the length is what increased, called linear strain, this side and this side we have linear strain, and this side, okay, this side and this side, what will have? Lateral strain, right? This is the linear strain, you can say. This is called lateral strain. This is called linear strain. All right now. So linear strain is done, lateral strain is also done. We'll talk about the volumetric strain also at the same time. So volumetric strain also you can, because volumetric strain always come into picture because of the change in volume. huh? So just like linear strain, lateral strain you have seen here, similarly we can talk about the volumetric strain. So volumetric strain, suppose now this is the one vessel here, okay, and inside this vessel, suppose we have filled, okay, we have filled air. The air has been filled here, okay. So air is what coming, huh? So what will happen? This air will come inside the vessel and it will create tension on the surface, pressure will be created, high pressure. So what will happen? This size will be increasing. Volume of this vessel will be increasing now. It becomes something like this. It becomes something like this, right? So the point is, initial volume for this is nothing but V. Now the volume has been changed. Just say it is delta V, okay, in all direction. So final volume, it becomes V plus delta V. Change in volume is nothing but V plus delta V minus V. That means delta V. What is volumetric strain then? It's a epsilon V. Change in volume delta V by V. Change in volume by original volume. Okay, that is called volumetric strain. Now this volumetric strain we can calculate for different section. Different value we will have. Okay, you are calculating volumetric strain for the cube, or you are calculating volumetric strain for the Cartesian coordinate system. You are calculating for the volumetric strain for the cylinder. You are calculating volumetric strain for the sphere. So definitely, because if you talk about the change in volume by original volume, so definitely for the Cartesian coordinate system, volume will be different. For the cylinder or for the sphere, volumetric volume will be different. So change in volume will also, you will get different. So based on this shape and size, volume will be changed. Hence volumetric strain will be completely different for different type of the cross section uh, object. All right, done. So this was related to the different volumes, that it was, you can say it was classification of the volumes. You have seen linear volume, that is also called longitudinal volume, and then you have seen the lateral uh, longitudinal strain, lateral strain, and then this is the volumetric strain. Means all type of volume strains you have seen. Okay, done. So what is the Hooke's law? Here we have to concentrate. Hooke's law. We have to talk about Hooke's law.
Press is directly proportional to strain.
Yes, right. But the condition is temperature, or in that the all properties, basically thermodynamics properties, that should be constant. Means temperature should not vary. Then only stress will be directly proportional to strain. Okay. So the point is, if you talk about the Hooke's law, then you have to check the material, and like there is limit which is called elastic limit. So first of all, you should know what is the elastic limit. So elastic limit you have to define once there is the elastic material. Otherwise, how you can define the elastic limit? So for elastic material, you have to check the elasticity. So what is the elasticity? It's very simple. So elasticity is the property of the material when any material which is loaded. Okay, suppose here this is the object, and this object is what carrying some load. You just say F load. Okay, so because of the load F, the shape of the object will be changed. What will be the shape? That length will be increased, something like this. Once load is what there, then the shape will be changed. Actual length is nothing but L. Okay, actual length is nothing but L, but it becomes now uh, delta L will be increased, so it becomes now L plus delta L. Hope you understood, right? Now, but again, because this is basically starting condition. This is the starting condition, or you just say F is here. F is what? Here F is what? 0. But here you have applied load F. Then again the same, again if you make, this is the first, this is the second, third case, again you, for the same block again you made the force becomes 0, means you remove the force. Here there was no force, here you have applied force F, and here again you remove the force, so again it will regain its original shape or size. Anything you can say, shape or size. So again it regains the same length L. So this type of material called as a elastic material. Okay, so in till elastic limit this will happen. So your Hooke's law, if you talk about the Hooke's law, so when you have to note of this statement, when a material is loaded, when a material is loaded within its elastic limit, elastic limit, stress is directly proportional to the strain. Proportional to the strain. Okay, so outcome of this is nothing but, how to write it, your stress is, okay, stress is directly proportional to strain. Stress is directly proportional to strain. That means sigma is directly proportional to strain epsilon. Sigma is directly proportional to the epsilon. That means stress is directly proportional to strain. And always remember, this will hold good for the, uh, all both type of load, maybe tensile load or maybe compressive load. For both type of load, it is hold goods. Okay, holds good for the tension as well as compressive load. All right, now coming to the final formulation of this. So once you remove the proportionality, you will have a constant. That constant is nothing but E, capital E. What is the capital E? It's called proportional constant. Yeah, it is
Yeah, it's
called,
modulus.
yeah, it's called proportionality constant, or constant of proportionality. It's nothing but constant of proportionality. Okay, which is known as known as modulus of elasticity, or it is also called Young's modulus, right? It is also called Young's modulus. Now, so final formula what you have here, it's nothing but sigma is equal to epsilon capital E. Okay. Now for any bar, okay, you just say, suppose this is the bar now. Here load P is what applied. Load P is what applied for the area of A. So what is the stress now here? What is the stress now? P by A. Okay. Once load P is what applied, so definitely size will increase. What is the size increase now? It's a delta L. What is the actual size? It is L. So P by A. What is the strain now? Change in length by L. Delta L by L strain. What is capital E? Young modulus. What is the elongation? Elongation means change in length. Elongation means change in length. So what is the delta L elongation? It's nothing but PL by AE. This is called PL by AE. You always remember, okay? For any prismatic bar, if you applied load P, so change in length is nothing but PL by AE. What is A? What is A? A is nothing but area, cross section area, delta L, PL by AE. Change in length or elongation or deformation. A is nothing but cross section area. What is A? Cross section area. What is E? E is nothing but Young's modulus. And obviously P is the load, actual length, and P is nothing but load. So everything is what known. With the help of this, we have to solve the numerical also. Okay. Now coming to the factor of safety, we'll also have to discuss the factor of safety, or we'll see the Young modulus formula also. What is the Young modulus? If we'll calculate the value of Young's modulus, okay. So Young modulus is nothing but E. What is that? It's a sigma by epsilon. Sigma by epsilon. What is the sigma? It's the Newton per meter square. Epsilon is dimensionless. So Newton per meter square also called as a Pascal. Okay. What is Newton per meter square called? It's a Pascal. It's a Pascal. Always remember, this is the unit of the Newton per meter square. Huh? It is also Newton per mm square. If you write Newton per mm square, okay, that also, if Newton per mm square is there, check. If we have a Newton per mm square, what is that? Newton by mm. In 1 millimeter, how many meters? 10 to power minus 3 mm square, so it's a square. It's a Newton divided by 10 to power minus 6. Now it becomes meter square. 10 to power minus 6 meter square. You can say Newton per meter square into 10 to power 6. The meaning is 1 Newton per mm square is equal to 10 to power 6 Newton per meter square. Means 10 to power 6 is nothing but mega. Newton per meter square is nothing but Pascal. So 1 Newton per mm square is equal to mega Pascal, 1 megapascal. That you need to remember. Okay, that you need to remember. Always. Correct. It's a not LMPa. This is the one. There should not be confusion. 1 megapascal. Correct. Now, before going to factor of safety and all, we'll also have to discuss about the, the Hooke's law. I have explained, but I have to draw the, diagram for the stress strain, which is also called stress strain diagram, and that stress strain diagram we are going to uh, draw here. It's a basically one experiment, tensile test, okay, universal testing machine, that we have, and we can get after this experiment, where you will have a one bar, and in that bar you will apply load. Suppose this is the bar here, see, this is the bar here, and over this bar if you are applying the load, over this bar if you are applying the load, then what will happen? See, obviously the length will increase once you apply tensile load. But this is not actual. What is the actual? Actual is length will increase, but at the same time diameter will also decrease, something like this. See that length is what increasing, but at the same time length is what increasing, but at the same time, see, this is what a thinning here. Okay, this is what thinning here. So the minimum area where the minimum area occurs in the bar called neck. Okay, so it's very clear now. Once gradually you apply, if you increase the load, okay, from 0 to gradual increment of this load P, okay, then what will happen? So we'll get graph that is called stress strain graph. Okay, that is called stress strain graph here. So I can give the name stress strain graph. Stress strain graph, or stress strain, that relation we have to show, or diagram. Okay, so how it looks like? It's very simple. The stress strain diagram is what, something like this. See, this is the stress strain diagram. Check. Once you increase load, the stress strain diagram will be something like this. Okay, once you increase this load P, okay, in the bar, so length will be increasing, that is true. And also the in between somewhere thinning process will also occurring, that is nothing but area will be decreasing. Okay, and where the minimum area will have, that is called neck also. And if you see the graph, how it shows, so the corresponding graph will be something like this. Okay, I am just directly drawing here. And in UTM machine you will get the graph. There will be monitor, and on monitor you will able to see this type of the corresponding graph. This is the graph now, something like this. Something like this. Okay, so I can give the naming of all, so you will be clear to you. This is called A. Each and every points I will explain, don't worry. This is B, this is C, this is D, this is E. Okay, this is what fracturing. This is the fracture point F. Okay, this is the fracture point F. Now you can extend this. So this is the maximum stress at point T. So hence it is called maximum stress, which means ultimate tensile stress. It's called ultimate tensile stress. All the points are very important here. Okay, so like one by one I will mention here, and explanation also will give. So point A is nothing but called as a proportional limit. It's called proportional limit. Then next point is nothing but B, elastic limit. Then what is the next two points we have parallelly? C, upper and lower, C and D. Now, upper and lower, it's called yield point. Yield points. This will be upper yield points and this is the lower yield points. C and D, upper and lower yield points. Then we'll go to the point E called ultimate stress point. Ultimate stress point. What is F? F is nothing but moto breaking point. Breaking points, right? Breaking points. So all points here I have shown you, A, B, C, D, E, F. Okay. Basically, two very important point. This here, whatever the strain here you will get, that will be called as a, or this curve obviously related to that strain also will have, that is engineering strain, and this curve called as a engineering, it's called a engineering stress strain curve. And what this called? This is called true stress strain curve. True stress strain curve. Okay. So all the points are important with respect to true stress strain curve. We will have a true strain that also we have to calculate. With respect to engineering stress strain curve, we'll have a engineering strain that we have to calculate. So each and every point is also very important. Like I can explain you, you have to listen, you will understand. What is the proportional limit? The from O to A. O to A is nothing but proportional limit. That is the straight line, if you see, straight and linear, and hence proportional limit is the limiting value of stress up to which stress is directly proportional to strain. If you see here, O to A, so only up to this sigma is directly proportional to strain, this zone. Okay, this is called elastic proportional limit, obviously O to A. And here uh, you can say that Hooke's law will be valid. Hooke's law will be valid in this region where stress is directly proportional to strain. Then what will be the point B? Obviously, it is also just point A. In few books, A and B are same, but here we have integrating different with different points. So point B is slightly beyond point A and is known as elastic limit. So up to point B, the material will regain its original size and shape when the load is removed. This indicates that material has elastic properties up to point B. All right, up to point B. Similarly, what is the yield points? See the yield points, basically C and D. C will be upper yield point and D will be lower yield point. So what is the yielding? First you should know yielding. So if material is stressed beyond point B, if you again increase the load and it is going beyond point B, then plastic deformation starts. Then plastic deformation starts. Plastic deformation means the material uh, once remove the load, then the material does not regain its shape and size, then it is called a plasticity. So once plastic deformation will be there, once plastic deformation will be there, that is called yielding. Basically, once plastic deformation occurring means once you remove the load, it will not regain its shape and size. Okay, so the point B is slightly beyond point A. You can see here in the diagram, this point B is slightly point A, beyond point A, and is known as elastic limit up to point B. But if you ahead to B again you go, then you will get the yield point. So each and every points are very important, you listen carefully. So from point C, plastic deformation starts. Okay, after C you can say, from point C or after C you can say, plastic deformation starts and the material does not regain its original size and shape. Okay, once it is unloading, that phenomenon is called as a yielding. So this is the upper limit, that is C, and D is nothing but lower yield point. Okay, so the lower yield point will be basically at point D, and what will occurs at lower yield points, a point at which minimum load or stress required to maintain plastic deformation, okay, called a lower yield point. And what is the upper yield point? A point, I'm talking about upper yield point, point C. So this is the point at which maximum load or stress required to initiate plastic deformation. So here plastic deformation start. Okay, start. Plastic deformation start. To initiate plastic deformation, what maximum stress is required? That is upper yield point C. Okay, and the minimum stress or load required to maintain plastic deformation called lower yield point, that is D. Remember, okay, listen carefully always. Then coming to point E, what is the point E? That already I have mentioned, it's nothing but ultimate stress point. E, check here, I already have mentioned, this is E. Now, so what is the ultimate stress? Always remember, ultimate stress is the point where the maximum load we have to apply to the specimen. Specimens, that object, that bar, what is the maximum load it can sustain without any failure? That is nothing but ultimate load, and that related stress will be called ultimate stress, and that point will be called as ultimate stress point. All right. Then next point is the fracture point, or sometimes also called breaking point. In this reason, or in this point, what will be happening? If you continuously increasing load beyond the ultimate tensile load, then necking will start. And obviously necking is already started basically, but beyond the ultimate stress point is reached, necking takes place. What is the necking? I told you that minimum area. Once minimum area you achieve somewhere, it is called neck. And necking means that at that point the continuous area will be decreasing. And obviously once you, after ultimate uh, stress, after point E or beyond point E, necking will start, but once it reach to point F, so that material will fracture, means it will break down. Once it will break down, then how it looks something like this. See, okay, it looks something like this is the bar, and here it looks something like, so here it's fracture or break. Okay, that is nothing but point F. I hope each and every points here I have explained, I hope it is clear to you, right? Okay.